So today we saw a result about triangles and then also a result that relates angles inside of a circle. So these are two big theorems. 1.3.3 that the sum of the angles in a triangle is 180 degrees, and 1.3.6 Thales theorem, or the Star Trek lemma, that relates the measures of central and inscribed angles inside of a circle. So 133 is our 180 degree result. And in order to prove that the sum of the three angles interior in a triangle add up to 180 degrees, or maybe a better way to say it is they add up to the measure of a straight line. Straight angle. And okay, we can call that 180 degrees, but what's important is that it adds up to a straight angle. In order to do that, what we ended up needing to do was construct that additional parallel line to add to our figure. Right? We could only construct that additional parallel line to add into our figure because we're taking for granted the parallel postulate that says that such a parallel line exists uniquely and we can construct it. Right? If we're not able to do that, then we weren't able to show that the three angles which we created that were sort of adjacent, the x, the y, the z, we couldn't show that, that those angles were in fact congruent to y and z, where we needed them to be congruent to y and z. But as long as we can construct that parallel line, then we had those theorems from 1.3.1 that related together the measures of corresponding angles, of alternate exterior angles, and of adjacent angles. And really, the only version of that we ended up using were the alternate angles. We showed that L and K, the angles which our parallel line made in addition to x, that those were congruent to the other two angles in our triangle because they were alternate angles to the angles inside the triangle. And so that connection is what allowed us to take the angles which we were interested in, y and z, and move them from one place in the figure to the other. Right? Find other angles in the same figure that had the same measure. And then since all three of those angles were now in the same spot, and because they together form a straight line by construction, then by construction the sum of those three add up to the measure of a straight angle. And if the measure of a straight angle is 180, that guarantees that the sum of our three angles is 180. But again, we focused in our discussion also on the role that the parallel postulate played here. Without the parallel postulate, we would either have to find a completely different approach to this proof, because we wouldn't be able to construct that parallel line, or there's a chance that we might not be able to find an alternate approach to this proof, because maybe the result's not true. Maybe this result actually depends upon the parallel postulate being true. Spoiler alert, it does, for reasons that we may be able to get a taste of later in the semester. But the parallel postulate is part of what makes Euclidean geometry Euclidean geometry. In Euclid's Elements, it was the fifth postulate out of 5 that formed the axiomatic system of Euclidean geometry. And what was interesting is that it's the one that's independent of the other 4. So we can take away the parallel postulate without screwing up the rest of geometry. And when we do, results like this one end up going by the wayside. And we get different angle sums inside of a triangle. And then finally, in 1.3.6, we prove the Star Trek lemma, that if I inscribe an angle inside of a circle, and inscribe means that the 3 points of that angle are on the circumference of the circle, then the measure of that inscribed angle is exactly 1/2 the measure of the angle made at the center of the circle, right, which is called the intercepted arc by the author. I call it the central angle at the middle of the circle. So there are actually several different cases in this proof that one would worry about. We saw one of the cases, and the other cases are not significantly different. So I invite you to review it in the book, but it's just rather than having exterior angles somewhere, the exterior angles are somewhere else. So there's not a substantive difference in the other cases. And this proof relied upon taking the diagram and cutting it in half. So drawing this line from A through the center of the circle at O, and cutting our Star Trek symbol in half, the way that we did right here. And in drawing in that additional line, what it ended up giving us that was really important is it gave us 3 congruent line segments. AO is congruent to BO is congruent to CO. And we knew that all 3 of those were congruent by the very definition of what it means to be a circle. A circle consists of all the points that share a common distance to a fixed center. Here the center is O. So because A, B, and C all lie on the circle, they all have exactly the same distance to O. But why that's important is that that makes for us a pair of isosceles triangles. AOB is isosceles because AO and BO are congruent. AOC is isosceles because AO and CO are congruent. And we just happen to know something, a little something, a lot of something, about the properties of isosceles triangles. Specifically, for this proof, we know that having equal side lengths also guarantees congruent angles that are opposite to those sides. That was 1.2.6. And that was the really important thing for this proof because it allowed us to conclude that the angles which here are labeled V and W, so this angle here and that angle up here, that those were congruent angles one to another. And ditto for our other isosceles triangle, the angle labeled U and the angle measured N.
And we know that because of alternate interior angles?
No, we know that because of the isosceles triangle theorem.
Oh, okay.
So there, because we don't have a transversal cutting two parallel lines here, we don't have the 1.3.1 alternate interior angle machinery, but we do have isosceles triangle machinery that we can call upon. But once we've established those, then all we had to do was relate the measures of those angles to the measures of alpha and beta, and that is where we end up using some of the 1.3.1 machinery. So alpha, actually no, I'm sorry, we use 1.3.4 there, which is a theorem about exterior angles to a triangle. So an exterior angle to a triangle has a measure that's equal to the sum of its two opposite interior angles. So alpha is the same as V plus W, beta is the same as U plus N. But then trading out a V for a W and trading out a U for an N because of the congruence of those angles allowed us to do the algebra that we see over here on the left. That takes us from alpha plus beta all the way down to 2W plus 2N, which factoring out the 2 gives us 2 times the quantity W plus N. And since W plus N together makes the angle ABC, or BAC, I'm sorry, that allowed us to make this conclusion.